Hello everyone. Our project is called PlayerPredict AI, NBA next season performance predictor. This is for CAP 4630 Intro to Artificial Intelligence class. Our team members are Ethan Sabeda, Andrew Naranjo, Frank Watkins, Edwin Feliz, and Jake Shuck. For this project, we built a complete AI system that uses machine learning to predict how NBA players will perform in their next season, based on their historical statistics. Objective: forecast player performance. What problem are we solving and why does it matter? Problem: NBA teams, analysts, and fans care about how a player performs or how a player may perform next season. A player's current season stats can provide signals about future scoring, rebounding, and playmaking. Accurate predictions drive rosters and contract decisions, give fantasy sports players a competitive edge, and fuel the growing sports analytics industry. Our system predicts three outputs: PPG, which is points per game, RPG, which is rebounds per game, and APG, which is assists per game. Project goal: build a machine learning system that predicts next season PPG, RPG, and APG from historical NBA season statistics. For our input, current season stats including age, games, MPG, per, TS percentage, USG percentage, WS, shooting, rebounds, assist, turnovers, and PPG. Dataset: NBA season statistics. Season level player records from basketball reference style historical data. We have four key numbers: 9,823 player season pairs after pre-processing, 1980 plus and later as our starting season filter, 20 or more minimum games played, and 24 input features. Raw data to cleaned player season data. Key columns used: player, year, age, games, minutes, shooting metrics, rebounds, assists, steals, blocks, turnovers, win shares, per, usage rate, and total points. Why season level? The project predicts next season production, so each row represents one completed player season, and the target is built from the following season. We started with 24,691 rows before cleaning. We filtered to 1980 and later because advanced stats like per and usage rates were not tracked in earlier decades. We also filtered to players with at least 20 games played to avoid small sample sizes. After cleaning, we were left with 9,823 clean player season pairs. Data preparation and feature engineering. Turning raw totals into model-ready predictors. Filter seasons. Keep 1980 plus and players with 20 plus games. Next, remove duplicates. One row per player per season. Next, create per game stats. PPG, RPG, APG, SPG, BPG, Top G, MPG. Next, build targets. Shift each player forward by one season. Next, train/test split. 80% training, 20% testing. Target construction. For each player, the model used current season stats to predict the following season. Seasons without consecutive next year were removed to avoid mismatch labels. Models used. Three regression approaches were compared for next season points per game. Linear regression. Simple baseline that learns a weighted linear relationship between stats and next season PPG. Chosen as a simple baseline to compare against more complex models. Next, Random forest regressor. Tree ensembles that captures non-linear relationships and provides feature importance, chosen for its ability to provide confident ranges in feature importance. MLP neural networks. Multi-layer perceptron trained with ReLU activation and early stopping. Chosen to test whether deep learning outperforms transitional machine learning. Additional outputs. Separate random forest regressors were trained for next season rebounds per game and assists per game. Methodology / pipeline. End-to-end flow from raw data to player forecast. We start with seasons, stats, CSV, historical season records. Next, cleaning. 1980 plus, 20 plus games, duplicates removed. Next, feature engineering. Per game and advanced metrics. Next, model training. LR, RF, MLP. Next, evaluation. MAE, RMSE, and R square. Finally, demo. Predict PPG, RPG, APG. Evaluation metrics. MAE and RMSE measure error in points per game. Lower is better. R squared measures how much variance the model explains. Higher is better.
Starting off, we have our exploratory analysis. The model learns from historical data patterns. We see here two graphs, the first showing the distribution of player scoring, with our x-axis showing player season, or y-axis showing player seasons, and x-axis showing the current season's points per game, and the next graph showing our current versus next season's point per game, with the y-axis showing our next season's point per game and our current season's point per game. We see here that most player seasons fall below star level scoring, creating a long tail of high point per game seasons. This is why recent scoring production is expected to be a powerful predictor. Our EDA takeaway is a player's current season scoring rate is strongly connected to the next season's scoring target, but age, role, minutes, and efficiency add context. Next, we have our implementation results for our points per game prediction model. These show the model comparison on held out test data. Here are three of our model performance comparison graphs. Our first graph is our MAE, where a lower score equals better. Our second is our RMSE, where a lower score also equals better. Our third is our R2 score, where a higher score equals better. We see the best overall R2 was MLP neural network at 0.7629, while linear regression was a very close second at 0.7625, and random forest followed at 0.7554. All models predicted the next season point per game within roughly 2.3 MAE. Here we see our actual versus our predicted performance. Our random forest predictions generally follow the actual next season's point per game trend. This graph here, we see the random forest versus the actual predicted with a R2 score of 0.755. Our y-axis shows the predicted next season's point per game by the model, while the x-axis shows the actual next season's point per game. The dashed line across the middle is the perfect prediction line for the model. We can see that our model does a great job by having most points centralized towards the perfect prediction line and not having any points too far a distance from the line. Our interpretation is that the predictions cluster around the perfect prediction line for most player seasons. Larger errors appear more often for elite scorers, where year to year role changes, injuries, or team context can shift production quickly. Some of the challenges that we face where injuries and trades are not captured in our dataset. We address this by adding a plus minus confidence range to communicate uncertainty. Our linear regression with R2 score of 0.762 and MLP neural network with R2 score of 0.763 showed similar scattering patterns to random forest. Our points per game model metric summary showed a 2.33 random forest MAE, a 3.03 random forest RMSE, and finally a 0.755 random forest R2. Now we have our key findings. Which features mattered most? Our random forest feature importance helps explain the model. Here we see the top 15 feature importances, with the y-axis being the actual features themselves and the x-axis being the importance score. Our top insight shows the current season's point per game dominated the feature importance score. This makes basketball sense because the strongest indicator of the next season's scoring is a player's most recent scoring level. Secondary signals included age, usage rates, minutes, turnovers, and win shares, all contributed smaller but meaningful information about role, opportunity, and efficiency. Here's our conclusion, our key takeaways. All three models predicted next season's point per game within 2.3 points. The current points per game was the number one predictor with a 74% feature importance. The assist model was our strongest at 81%. Confidence ranges make our predictions transparent and honest. What we learned. We learned that the raw data went from 24,691 to 9,823 rows after cleanup. We learned that simple regression matched the complex MLP. We learned that feature engineering matters more than model complexity. And finally, we learned that responsible AI means showing uncertainty, not just a number. Future work that can be done for our dataset. All of the data in our dataset ends in 2017. We could add recent seasons for players such as Luka Doncic, Giannis Antetokounmpo, and Jason Tatum. We can include injury history and team changes as features. We could also expand the web app with real-time NBA data from 2018 to 2025.
This is our project UI, and in this data set, there's over 1,700 players with nearly 10,000 individual player seasons. Here you can see the model performance using linear regression, random forest, and MLP models. And this shows the feature importance and some high scoring test samples. And here you can search up an NBA player's name, and you can select any of their seasons, and it'll load all their season stats here. And you can also input your own stats here if you choose. Predict next stats, and this will show the predicted stats for next season. You can see it shows different models, and it shows points per game, rebounds, and assists. And here's where it shows some graphs and more info on the data.